introduce our second keynote speaker. Please join me in welcoming Shirley back to the stage again. 接下来呢，我们再次有请侯晓玲执行长为我们介绍今天的第二位主讲人 Shirley.
Last but definitely not the least is our next speaker, Dr. Jay Lee. Dr. Lee is a Clark Distinguished Professor and Director of the Industrial AI Center in the Mechanical Engineering Department of the University of Maryland, College Park. He's leading AI Data Foundry for advanced data-centric AI research for diversified industrial systems. Previously, he served as the Ohio Eminent Scholar, L.W. Scott Alter Chair, and University Distinguished Professor at the University of Cincinnati. He also served as Vice Chairman and Board Member of Foxconn Technology Group. In addition to receiving countless awards, he also published Industrial AI book in 2020. Smart Manufacturing Magazine named him a top visionary in 2016 and one of the most influential professors in 2020. I cannot possibly name all of his accomplishments in the time that's here. So without further ado, please welcome Dr. Jay Lee.
让我们欢迎工业大数据专家、马里兰大学讲座教授及工业人工智慧中心主任李杰博士。Next, we're going to have Dr. Jay Lee, Clark Distinguished Chair Professor and Director of Industrial AI Center, University of Maryland. And he is also quintessentially world's leading expert in industrial big data. 那这个李博士讲完之后呢，就是我们最后的 Q&A 时间哦。到时候都欢迎各位贵宾可以提问，我们也会再次的邀请今天的所有的讲者回到舞台上。And now over to Dr. Jay Lee. Please give him another big round of applause. Thank you.
Thank you. Yeah. Well, thanks, Terry and the Yongling Foundation for inviting me to share with you some real examples that we have to do for industry, right? AI is always interesting, but you also need actual implementation, right? So today I will share with you what are our experiences and what are the gaps that we need to move forward, right? But especially look at the future trends of a data-centric economy when systems are connected, the modern world. We have lots of data more than you and I needed. But how much data is useful and how much data is usable? Not all the data is usable, right? And second of all, do we have to use a $1 million investment for AI to solve $1 million problem? Or can I use $1,000 AI spending to save $1 million industry saving? We call this a non-traditional asymmetric machine learning. We learn from the war, right? Asymmetric warfare. $3,000 drone can damage hundreds of $1 million ship. Why not AI? So let's look at the trend, right? AI started in 1955 during the natural language processing, so human voice data, image data. Then machine, robots, machine tools, chillers, elevators, jet engines, wind turbines, EVs. So eventually you have a 3D, right? This is a large language model, more and more now coming. But next is a large knowledge model. Knowledge is broken. Your knowledge is different from mine. But if we work for same companies, we gotta have overlap, right? So how do we cherry pick the best one to assemble them to the right one? Of course, when you combine all the source of data from history, from sensors, then eventually the data becomes so rich. Then the question is, do you want to use all the data to do a always deep learning, or you want to have a simplified learning? Eventually, of course, from many companies like NVIDIA, for example, say, oh, I'm going to sell AI as a platform. Maybe one day data center going to have a GPU, so everybody can do AI in the cloud space. But that's what the foundation platform is, right? If that's the case, the question will be, how about this? I got hundreds of thousands of jet engines flying in the air every day. I flew in 777-300, probably either GE 90 engine or Pratt & Whitney 4000 engine, right? So eventually our GE last week said, oh, we're going to have a 90,000 engine flying and 50,000 wind turbines. Wow. So you got a bulldozer everywhere and EV like Tesla everywhere and modern foundry. You got all the modernized 7 nano, 5 nano, 3 nano, all the very expensive conveyors and the Daifuku, all the conveyor and all the expensive machine UVs. Everything connected, right? So the question will be how much we know, how much we don't know. So even the question will be domain knowledge. We, human beings, we always know what we know, right? So we drive experience. For example, Kaizen, continuous improvement. It's based on alarm, create problems, then we continuously improve. One day, we have a good model I can avoid. Unfortunately, the baseline different, the experience cannot be used. Or I can learn, but I cannot duplicate. Of course, more and more for large system, for example, like you have a aircraft flying in the air, if weather continue changing, but how can I save fuel based on large data sets coming in, right? Wind turbine, the mountain turbine, at night, you have a low temperature, high humidity, you have ice accumulating on the blades, reduce your power generation. You got like ship, right? We worked on a ship before, right? You have a weather, wind, and the wave, 3W, continually changing. We can navigate, learn the drag force, and save 6% of fuel per year. 7, 8 years, you can buy a new ship. You got a fish farm, how to measure the bacteria, and how can the pH value of the water eventually have a healthy fish. So all the invisible we don't know, but eventually how to avoid them. So this is what we're talking about, right? How we kill the blue area, which is going to be a large return in centuries to come. Because you and I probably will be gone, but airplane continue coming. So therefore, one way is new better data representation. When we have large data, we have less data. The method is very different. I have less data, I can control design experiments. We have large data. Wow, I can do all kinds of clustering, but I can do topological analysis, right? But the problem is the purpose, not the problem, not the process. So we take, for example, TSMC data sets, and this is about 800,000 data sets, right? So this is the wafer yield. After that, so what's the purpose? I don't want to see all the problem. I want to see what can I do to avoid that. Wow. So I can simplify that to a very simplistic view, how to take action, not to understand the problem. Action is more important, right? So eventually, we're talking about the data set now. In industry space, the knowledge is broken, right? So we have a large data. If someday you have a useful data, congratulations, you're in a great shape. Unfortunately, most of the time, we have useful data, but not usable, right? You donate the blood, you have HIV, you have hepatitis B, your blood is not usable. Useful, but not usable, same thing. Eventually, sometimes you have useful data, but not useful. I'm sorry, bite the bullets, use it, squeeze it, right? Every juice count, do something. Or, of course, you should not continuously collecting data not useful. Unfortunately, lots of companies today continue doing that every day because they think someday there's a magic AI will be there to solve their problems, right? So therefore, we know something well, we build a response service approximation called RSA. This is my problem. I can model it, right? So eventually, I have lots of data for the baseline. I build it. But during the actual applications, might be local problems. It's okay. I only select those useful and useful data, small data sets. I can build much better, much useful decision-making process, right? So eventually, we're talking about what are recent advances. We normally learn from the last 20 years from old machine learning world, right? And now we're saying, well, we have lots of non-traditional problem now. We have to start using asymmetric machine learning. So this is something we call intelligent metrology system. If we can take a data-centric system as a metrology system, today, if somebody asks you about metrology system, you think about it has to be a laboratory, very protected environment, very precise machine, control temperature, everything perfect. No, I'm talking about metrology is a measurement system, powered by the hour. You measure jet engine flying now. You cannot take off the engine, right? Wind turbine running in the field. How do you measure relationship between the wind and the power generation? So you have lots of data coming in, sensor, but we gotta create a large model from the broken source. Humans, digital twins, design, big data, simulations, right, models. Eventually, we give the human final tweak to make decisions, right? So machine learning, AI augmented metrology in the real world, real time. So eventually, one thing we're talking about is transfer learning. When you have a large number of equipment, large number of fleet in the field, you cannot always collect all the data, train all the model. That's not economically viable. Even you can do so, the time will be wasted. Eventually, transfer learning becomes a very common way to do it, right? Of course, some domain, some machine work on welding, some machine work on painting, but how can I see my motor behaviors, right? Same thing for the vehicle. I have a vehicle. If you're a Tesla driver, I am. I also bought a Tesla insurance. Tesla hired three of our PhD before, 2 left, 1 joined Wall Street, another one still there. Hey, this is exactly vehicle to vehicle, human to vehicle. How I drive, my behavior. When you buy insurance from Tesla, they can judge you based on aggressive driver, how you take turn, how you signal lights, right? Eventually, this is exactly what happened. Tesla announced, called the FSD beta version V12, August 26. I think you remember 2 weeks ago, the stock valuation, 10%, $860 billion, right? Because it saved 90% of code. They use a good driver's behavior to train a system, not just use the camera itself. That's why sometimes they say, oh, I really don't need a LiDAR, because they have all the data from a driver who bought insurance. Well, I'm one of them, right? This is a natural way of thinking, how to borrow things, accelerate the training, right? So eventually, one day, your phone has about a dozen sensors. EV has about 10 times, right? You have a lot of sensors generated from your driving. When I hit a pothole here, I label the GPS and some vibration sensor. The guy behind me, 2 miles ahead of you, pothole, be careful. It's gonna happen. Today, like Waze, you have to input by manually, right? So in the future, you're gonna have automatic generated label data based on the moving equipment, moving machine, right? Could be satellite-based. So I'll give you some case study because time. So you have 4 areas, which call factory, facility, fleet, and field. I call the 4F. Typically apply to all industry, like oil field, right? Wind turbine field, right? Factories, foundries, right? Hospital facility, et cetera, et cetera. So let's use one example, high volume manufacturing, right? Semiconductor. We've been working on semiconductor for over 20 years, right? Intel was my first founding member. How we started? They gave me a vacuum pump. Wow, lots of vacuum pump in clean room, right? But when vacuum pump fail, that's not good. How can we worked on the Fab 22, Chandler, Arizona, right? That was the first fab, right, we worked on. So after that, you start moving in to SRC, Samsung, CVD, and AMD, Sematech, then the Global Foundry, Applied Material, Etcher, and the Lam, right? And the Hitachi High-Tech. We train a TSMC engineer. And today, we're still working with Winbang, UMC, and of course, Hitachi High-Tech and Applied Material. Over the last 20 years, we learned big lesson. But in a lot of fab industry, right, in the modern fab, 7 nano below, yields big challenges. And we're still using design experiment, DOE. It's a good method, but it's very hard to reproduce it. You do, I do, very different. When one parameter comes, then we have to rechange it. Eventually, we developed a new digital twin method, faster, faster, better, right? So eliminate try and error. So this is very important. If you can speed up the calibration, you have a better volume production, higher yield. Of course, you make more money. There's no doubt. Can't imagine, right? Second thing is that when I was in Vice Chairman Foxconn, Terry was founder, right? He said, hey, let's do something to make our manufacturing become more transparent, more predictable, right? Predictable, that's what he said. So the FRI was formed 2018. So we had the opportunity to work with the business unit and say, hey, let's do something. We connect a machine for the right reason. We can monitor, we can predict. So one of the things we've done is that one of the things called stream of quality. In Terry's old dictionary, there's a 6 flow in manufacturing. He always say there's a material flow, people flow, and process flow, which are real, visible. But there's a money flow, information flow, and technology flow. They are virtual, right? But the 6 flow together, you can really know what's going on. You can pay worker every day. Can we all say that, right? That's exactly X. It's a stream of X. I can, using blockchain, stamp exactly each process, right? Human, materials, machine, method. Eventually, I can look forward, predict. I can look backward, trace root cause. When customers they don't have to have a station inspection for your product. Don't worry. You got the product, you can trace back, you can look forward. SMT line, you can save lots of money, right? So one factory we did was a World Economic Forum. We said, well, let's try something. So a lot of people walk around the factory every day. They also worry about end-on alarm. Well, why you worry about it? So we can predict, you can save a lot of redundant labors. That has been famous, right? Foxconn lights out factory. Lights out factory means worry-free factory, not no people factory. There are people there, but no worry, right? That's what it is. Of course, eventually, so far, there are about 132 lighthouses worldwide, but Foxconn has 6 of them. I know internally, probably I stepped down board member last year. I think the internal probably 20 to 30, similar, but certified by experts. But second case, large fleet base, right? So you have a wind turbines. Wind turbine, wind keep changing every second, every minute, right? So rather to monitor so many wind turbines, you're gonna have a huge data center. No, you're not gonna do that, I'm sorry. We rank wind turbine based on every wind speed changes. I can rank them how good, like a professor ranks student. I give a quiz 1, quiz 2, quiz 3. After 3 quiz, I know top 10%, bottom 10%, exactly. After different wind speed, I know exactly the left side is a high performance turbine, right side is a low performance turbine. Then I try more wind speed to see lowest performance. Then I do machine learning, only for 1 turbine. Save me lots of time. This is the pattern, yes. I presented it to GE last week. I said, wow, this is interesting. So eventually, we have different power generation. You have different wind speed, like time machine clocked, right? I generate, so each wind speed, I can look at the difference, eventually identify those low performance ones. I don't have to use the data all the time. Eventually, I can schedule based on the power loss. I can maximize my maintenance efficiency, and I can eventually schedule the crew, the vessel, the time, and the weather, of course, right? If the offshore turbine weather not good, the vessel cannot go out. So again, this is very interesting outcome, and it's been adopted by quite a few companies. So eventually, left side is the data side, right? Right side is decision side. You can integrate into one model, digital twin, right? Okay, time. Hospital, ICU. We lose patient every day. I lost my brother-in-law several months ago. Brain, we call brain TBI, traumatic brain injuries, right? So if you have patient push into they drill a small hole, put a sensor in there, then you have all the sensors monitoring you, right? Eventually, alarm happen, then nurse rush. The doctor coming, too late, gone. Most of people. Doesn't matter, you're rich man, you're poor man. same equipment, same machine. Of course, maybe nicer room, but lots of data. There's no intelligence, let's be honest. The plug and play is what it is, right, today. So eventually we say, oh, there's a human expert out there called SME, subject matter expert, but there's a ICP pressure, EEG signals. We can use a different type of a fast way to compare different patients, right? Because you have a 20 patient tonight. I cross training, I can find out the high-risk patient. Yeah, the TBI, ICU. So doctor can look at the number, tweak. This is a overweight person. This is a different child, as a kid. This is a different old people. So I can find those features that especially important for those patients, tweak them, right? Eventually make this become more customized from human side. Then I took a 43 ICU real patient data. We work with the Cincinnati Children's Hospital, which is number 2 in the country. First one's Boston, second one's Cincinnati, right? So you can look at 43 patients, some recover, most people moderate recover and severe disability. But if you look at those people passed away, some of them had a very strong survivability, but the family didn't know. They pulled the plug. That's what happened. So eventually, took 3 years. Doctor said, don't publish. 3 years later, said, you know what? This is very useful suggestion, not decision. Decision still doctor and the family. So this is interesting. 2 weeks ago, I was in Japan. Japan Air launch.
So it boosted ignition and liftoff.
So after launch, then they destroy it, right? Because of certain failure. Right? So eventually, the reason I know. So Japan NASA called JAXA finally said, oh, let's get data together. Let's do a competition. They did. So they said, okay, we got a lot of solenoid, lots of valve, a lot of happening. So can you detect something? It's not normal. More and more rocket going to be reused, right? Like SpaceX. So it's very important to understand life cycle system. So based on you need domain knowledge, right? We are mechanical engineer. I don't know about you. The valve, from the moment you trigger, by the time they open, 0.1 seconds is very important. Then eventually you have a control, PDF, PID loop, whatever. So we take a dynamic time warping from the 0.1 second. You can quickly develop a good reference baseline. Then you have a similarity-based approach. So our team, 100% number 1. Of course, team 2 is 9.94. Even 1% is not allowed, right? 0.1% even not allowed. Why? You're talking about aerospace. So my PhD student, he was sent by Komatsu, Japan for 5 years of PhD. 1 year ago, he didn't know anything but diesel engine. Now, he's a good data expert, especially machine learning, using non-traditional, right, the time. So previously, we worked with a Taiwan other company like Haiwan, Eric, right? So they demonstrated Industry 4.0 board school, 2016. And the Coulson machine, they had a soul. When they sell the machine to other, people have to start watching the machine, cost money. I say, can you remove the worry out? Finally, we use a self-organized map and eventually can predict. So that the company from 2013 ranked number 10 became number 1. And there's the sleep, from sleeping management, eventually how to analyze what the quality of sleep. All right. So I mean, there's a few examples. So finally, summary, big time. Highly connected system, like what we're talking about industry, lots of data, it's true. But we got to know how to select the usable data, right? Otherwise, you'll be buying all the expensive equipment. Probably you cannot save money. Number 2, non-traditional machine learning, sometimes much useful, sometimes, not all the time, right? Depend on the knowledge domain you have. The similarity-based approach often can improve machine performance, right? But you need a systematic way. You cannot do try and error. So one of the challenges of the future for AI industry is that 20 years later, 10 years later, how does young people going to maintain your software? Big problems. Big problems. I don't even know how you code. I couldn't even debug. Big problems. You need to have some life cycle system in place. Not forget about how true, So it's very important to. So one thing is that AI is the actual implementation with speed and scale and systematic approach, not try and error. So that's exactly what my center is. I train engineers. I'm teaching industrial AI. All my students have to do jet engine, battery, semiconductor, right? Pump. All students. I don't know. What? Do it. You do it, you have confidence. You know. So eventually, you have data, computer science, domain is a purpose. But discipline is a process. How you learn, how you do. It's not by surprise. Right? So of course, this is a book, probably 2 years ago, but it's time to revise again. With a lot of new stuff going on, it's true. So previously, I also published a few books in Taiwan. The first one is by Commonwealth, and the industrial big data, and also industrial AI. I think it's some good reference if you're interested. Finally, you can look at our website, get some more information. Again, thank you for your time. Yeah.
Thank you so much to Dr.